Hello, I'm Ron Espiritu, and I worked with the members on screen to complete the third design assignment of the semester. The task of our assignment is to maximize the capacitance of a parallel plate plus dielectric capacitor system. The dielectric plate has a given electric permittivity, and all the components have a given length and thickness. We were challenged to manipulate the width of the dielectric plates and the conducting plates in such a way that maximizes the capacitance while staying under a specific total mass and width restriction. The densities and size restrictions are as seen on screen. I'm mainly focused on building the FlexPDE model and validating the simulation. We simulate the capacitance of our model to be equivalent to the charge on the conducting plates divided by their voltage difference. We also use this relationship, which incorporates the permittivity, plate area, and the separation to verify our model. However, this equation does not account for a fringing field and differing plate areas. We built our flex model by building the geometric shapes, and we then simulated the conducting plates and the dielectric regions by defining their permittivity and their expected charge densities. We utilized these equations, which are derived from Gauss's law and Coulomb's law. As previously stated, we define the geometry of our boundaries and the properties associated with them, being sure to create a surrounding region to account for their fringing field. One important relationship we leverage takes advantage of the densities and the width constraints. With this knowledge, we can rewrite the width of one plate in terms of the other two. Furthermore, we define rho naught, an arbitrary charge density of the plates. We set it to be arbitrarily high to simulate the activity of a conductor. One important bit to note is that our overall simulation leverages symmetry along the plane dividing the plates. Our calculation remains the same, but we are now only measuring half the capacitance and must calculate the restrictions with half the mass. We did several test cases. Once we built the geometries, we ran a simulation to check if the field fringes as we would expect at the edge of our capacitor plates, which it does. We ran a test to check if the capacitances from both the previously stated equations are similar when the areas are similar relative to separation, which it is. We also ran tests with a full geometry and a half geometry to check if the capacitance relate with a factor of 2, which they do. We also ran a test to check if a quarter geometry was possible leveraging another symmetry plane, and it doesn't. And this makes sense since the plate areas are not always the same, and therefore there is no plane of symmetry in the horizontal axis. We also did a test case checking that increasing the dielectric permittivity reduces the electric field, which is a property of dielectrics, and it does. Prior to scripting, it's important to note that because the permittivity of the dielectric increases the capacitance of the system, we'll expect a higher capacitance with a bigger dielectric, minimized airspace, and a maximized plate width. The scripting, like previous DAs, uses string manipulation to automate the simulation of running FlexPDE with several different widths. Our initial goal was to use grid search, in which we started with an arbitrary range and step size, and use the scatter plot output to precisely zoom in on our range until we see an extrema. To optimize, we made our Python script run two functions with the goal of using a gradient ascent to find the maxima. So let's break down both of these functions. The f function opens and runs the flex code with string manipulation and returns the simulated capacitance. These lines here search for the csim string value within the outputted text file. The grad function finds the gradient of our capacitance, and we later use this in our gradient ascent. The functions are implemented here, with R1 being the initial pair of widths, and we can redefine R2 using the grad function and the R1. If the capacitance using R2 is higher than R1, we know we pass an extrema and end our gradient ascent search. Given the constraints, the maximum capacitance we were able to come up with is 43.6 picofarads. This occurs at 0.01952 meters for the positive plate, a width of 0.01834 meters for the negative plate, and a width of 0.01958 meters for the dielectric plate. This value fits with our prediction that the capacitance maximizes when there is little air and maximum area between the plates.